Assalamu alaikum warahmatullahi wabarakatuh. My name is Mohammed Al-Waqedi from Section 1 DSP. In this assignment, the goal is to clean a noisy ECG signal and analyze the effect of the filtering process using various tools including time domain and frequency domain analysis. Corrupt ECG signal X noise. This is the noisy ECG signal that needs to be cleaned. The noise could arise from different sources like muscle activity, electrode motion, or environment interfaces. Visualizing the noise signal. The noisy ECG is visualized in discrete time and continuous time plots to understand its characteristics and observe the noise. Filtering method to remove noise. FIR and IIR filter are used. Each method follows a structured process that includes designing the filter, analyzing its frequency response, and applying it to the noisy ECG signal. FIR, which is referred to finite impulse response filter. The FIR filter is designed using a Hamming window. Filter design. The specification for the FIR filter are passband edge frequency 500 Hz, transition width 0.1 kHz, sampling frequency 10 kHz. Filter order 330. Impulse response. The impulse response of the FIR filter shows how it responds to an impulse input. This is a way to verify the filter's design, which is, as we can see in the code, plot WF percentage of plot the impulse response. Frequency response. The frequency response shows how the FIR filter attenuates or allows frequency. Key observation. Frequency above 500 Hz are attenuated effectively. As we can see, Freg Z W of 1 percentage of float the frequency response in MATLAB. Convolution. The noisy ECG signal is filtered by convolving it with the FIR filter coefficient, as we can see in the MATLAB code provided here. Pole zero plot stability check. The poles and zeros of the FIR filter are visualized in the Z-plane to assess its stability. FIR filters are inherently stable because they only have zeros, no poles. IIR, which is referred to infinite impulse response filter. The IIR filter used a second-order Butterworth law pass filter. Filter design: cut-off frequency 500 Hz, sampling frequency 10 kHz, filter coefficients. Frequency response: the frequency response of the IIR filter shows how it behaves in the frequency domain similar to the FIR filter I mentioned before. DT, DTFT spectrum, the discrete time Fourier transform, is used to analyze how the filter suppresses noise in the frequency domain. Convolution: the noisy signal is convolved with the IIR filter coefficient to produce the filtered signal. Pole zero plot stability check. IIR filter may have poles, so a pole zero plot is crucial to check stability. The poles should lie inside the unit circle for the filter to be stable. Clean ECG signal after filtering. The noisy ECG using both FIR and IIR method, a clean ECG signal is obtained. The clean ECG is visualized and compared with the original noise signal to confirm noise removal. Frequency domain analysis. Frequency response shows how well the filter attenuates unwanted frequencies with preserving the desired signal components. DTFT spectrum, the spectrum of the noise signal and the filter signals is plotted to ensure the desired frequency are retained. Also, corrupt ECG signal, noisy signal in both time and frequency domains, filter signals, comparison of FIR and IIR filtered signals in the time domain, impulse response, FIR and IIR filter responses to an impulse input, frequency response, how FIR and IIR filters behave across different frequencies, Ball zero plot the plane stability analysis of FIR and IIR filters. So as we can see here, the FIR filter achieves noise removal with inherent stability and a linear phase response, but it requires a higher filter order and more computations. The IIR filter achieves similar result with a lower filter order, making it computationally efficient. However, its bolts must be carefully analyzed for stability. Both filters successfully clean the ECG signal as evidenced by the clean output and the frequency domain analysis. Thank you. That's all.